Okay. All right, and let me share my screen.
Okay.
All right. So, yeah, let's start out here. So which one did you have a question with? Maybe number the first one? Some people had a question about that one, the energy one.
Is that similar to what we did in class?
Yeah, it's probably easier.
Oh,
Um,
okay.
let me just mention something here. I mean, okay, so let me bring that problem up. Okay, yeah, so it's all right, yeah, so we have to, let's see, get my pen here. Yeah, so it's this one right here. So we have to consider a mass connected to a spring. We have our equation here that models the motion of the mass on the spring. And we're supposed to derive an equation for the kinetic and potential energy and show that it doesn't vary over time, right?
Yeah.
So, all right, so you have to remember kinetic energy is 1/2 mv squared, right?
Yeah.
Okay. And so what's the v going to be in this case?
Uh,
Relating it back to this equation here.
X prime of t.
Right. So it's going to be 1/2 mx prime of t squared.
Right.
All right. Now what's the potential energy going to be?
Let's see.
That's a little more subtle.
Yeah.
Well, you have to go back to the fact that for a spring, if we're using, when we derive this equation here for the
Yeah.
motion for a spring, well, you did it in differential equations anyway. Um, remember, you started out with Hooke's law, force F equals kx.
Oh, yeah. Yeah.
All right. So force, the amount of force you have to use to stretch a spring, x units from its natural length, is k times x, where k is your constant of proportionality. Okay. So then remember that if you have a force acting on an object through a distance, the amount of energy that you use to move that object is the integral of your force function. Okay?
Yeah.
All right. Now, so our potential energy is this is basically going to be our potential energy here.
Okay.
If we take the spring and we stretch it, move the mass, the
Yeah.
mass stretches it downward. Okay, so now there's some potential energy build up in that spring because it wants to pull it back.
Right.
Um, the amount of energy, potential energy it has, is given by this equation right here. Okay, so when the mass is moving, it has the kinetic energy and it has the potential energy. The potential energy is bound up in the spring. Okay, and it's given by this. Okay, so it's going to be
Okay.
the following. So it's going to be the integral from 0 to x of t, okay, times k, and we're going to use a z dz, where z represents, z is an integral that we're integrating with respect to. And technically, it's the absolute value of x here.
Okay.
Okay. Now what you need to do, okay, so energy equals kinetic plus potential. Now, if we want to show that this is constant over time, how can we do that? What do we need to show? That it doesn't,
Uh,
it doesn't change over time, so we need to show what?
its derivative equals 0.
Its derivative equals 0. So if we need to show d dt of E is equal to 0. Okay,
Right.
so what you need to do is differentiate this guy right here with respect to t. Differentiate that equation. And you also need to differentiate this equation with respect to t. Now, for the absolute value, that's a little tricky. Break this into two parts. You can break it into two parts when x is greater than 0. So then you just get rid of the absolute values. And if x is less than 0, then just use the fact that the absolute value of x is negative x. Okay?
Yeah.
So, say, okay, I'm just going to assume x is positive. Okay, so then you differentiate, just get rid of the absolute values here. Differentiate this and show that you get 0. And then say, okay, well, suppose x is less than 0, then replace the absolute value with this. Differentiate with respect to t. Now, you got to be careful. You're differentiating with respect to t, not x, okay?
Yeah.
And you're also going to need to use this equation right here will come into play. And so you'll see like an x double prime pop out of here somewhere. Wherever you see an x double prime, replace it with this, and then everything is going to cancel out and give you 0.
Okay.
Okay?
Okay.
And so that's how this one works out. Okay?
Okay, and when you do the integral of p with d dt,
Yeah.
sorry, how did you do that one again?
Well, okay, so d dt, okay, so suppose x is positive here now.
Yeah.
So d dt of an integral from 0 to x of, now x is a function of t, k z d z. Well, I'm just going to move over here. So what you have to do is that's going to equal, you have to do the chain rule here. You have to let this be a u. Okay, so, well, no, just let it be an x. Okay, just say u. Just say x. So what you have to do is that's going to equal d dx of the integral from 0 to x k z dz times dx dt. Right?
dx dt.
See how the dx is canceled?
Yeah.
Right? You see, and then you get d dt of this quantity back. Okay, so you know you're doing your chain rule right.
Yeah.
Okay? And the reason you need to do this is so that, you see, these terms have to match. This x has to match what you're differentiating with respect to in order to apply the fundamental theorem of calculus, right?
Yeah.
Okay. So then, now this is just going to be the fundamental theorem of calculus. So can you tell me since we're here, what's that going to equal? This term right here.
It's just going to be kx.
Kx.
Yes, kx. Yeah.
And this term right here is going to be what? Just
1. No, I'm sorry.
No, 1. Dx dt, not dx dx.
0.
No, not 0. It's just going to be x prime.
Oh, right. Yeah.
You see, now you can use, your equations here. You see when you see the k right here is going to have an x prime in it, and these two terms here, the k and the p, will cancel each other. Well, when you differentiate, okay.
Right.
Inside of here, you're going to have things are going to cancel now.
Okay.
If you employ, and you also have to remember to employ this equation here, and things will cancel very nicely.
Okay. That's easy enough. Okay.
Okay. All right. And then what else did you have?
Number 2, I was looking at, I got stuck when it was like doing the initial condition.
All right, let's see. I'm just going to look back at, use the notation we did in our notes here. So for that one, let's see. If you look back in your notes, you should see this. Let's see. So that is very similar to this one that we did in our notes. so let me clear all this out. A little small, so I can write. All right, so for number 2, if you look back in your notes, we did a problem like this, right? I believe I used a Z instead of a U, okay?
Right.
But let me just use the U. So there's one in your notes where we did exactly this. U. Subject to the initial conditions. Right?
Yeah.
Okay. So basically, number 2 is the exact same type of problem. If you follow through your notes, the negative C is a 5 and
Yeah.
the F is an E, right?
Yeah. E to the X.
Right?
Yeah. Yeah.
Okay. So, now let me see. Is that the one? Oh, wait a minute. Maybe we did do that one. Right. Right. I modified my notes a little bit when I explained it to you, so I don't have that exact problem in here, but I believe we did that one, right? Isn't that in
Yeah.
your notes?
Yeah. We did. Yeah. Yeah.
Okay. Yeah.
I'm just looking at it a little bit.
Yeah. And so what we had to do then, yeah, okay, here it is. Okay, I did find. Okay. So you know what? Yeah, so what we had to do is we, describe those coordinate transformations. And we want to basically turn this operator into this operator, right?
Yeah. Yeah.
Okay.
And then
Right there, right? And so, what we did then is we, if you look through your notes, you'll see you come up with these equations here. I'm just going to cut this a little short here. So you see you come up with this piece right here equaling now the negative C here for this problem is going to be 5. And then partial Z with respect to S. And that's going to be times like that, right?
Yep.
All right, so that is in your notes now, right? And I went over how we got this equation. And so now what we want to do is if we want to turn this operator here into this one, then we need to choose this piece right here. We'll choose that to be 1, and we'll choose this piece down here to be 0, right?
Yeah.
Okay. All right. In which case then now we let partial W with respect to X, we let that be alpha. Right now we just picked some constants, so we said this. Partial W with respect to T be beta. Partial S with respect to X is gamma. and partial S with respect to T is a delta we chose to be, okay?
Yeah.
Now these are just going to be constants, right? And so if we have these equations up here then that implies that we need, now the C here is going to be 5, negative C is going to be the 5, right? That's what I said. So for your problem, you're going to have 5 alpha plus beta must equal 1. And 5 gamma plus delta equals 0. Okay? Now you have freedom to choose the alpha, beta, gamma, and delta.
Yeah.
Right? Okay. Right. And so I think, what do you think you want to choose the alpha to be? How about if we choose the alpha to be what?
Alpha, let's do 1 for alpha.
Yeah, well, how about maybe 1/5 and the beta be 0, right?
Oh, right.
Okay.
Yeah.
So let's see. Yeah, I'm just deciding right now if I want to let those, choose those yet. You know, we might not want to do those to the end of the problem. Let's just let those alone for now. Sometimes it's better to go to the end of the problem and then choose what they are, okay?
Okay.
I think we could do it right now, but just to play it safe, we'll choose those at the end. Now, what we want to do now is, turn this equation right here. We want to change this equation up here. So now we're going to choose the alpha, beta, delta, and gammas, assuming they're going to satisfy these equations down here, right?
Yeah.
You're going to now turn that equation into partial z with respect to w equaling 0, and that's going to imply that z equals some constant, which is just a function of s.
Yeah.
Okay? All right. And I think in my notes, I usually pick that to be like a g of s. Okay? Just some function. It's going to be some function of s. You see, so if I differentiate this with respect to w, I get back 0. Now, the s, let's see, from my equations back here, what is our s?
It looks like you have S.
Yeah, the s is going to be the gamma, right? I didn't write that out back here previously, but you see, yeah, from these equations right here, the w equals alpha x plus beta t, and the s is equal to gamma x plus delta t. Okay, I didn't write that out. So now my s, that's what you get when you solve these equations back here, you know.
Yeah.
So then this is going to equal g of, and let's see, so it's going to be gamma x plus delta t, right? Okay. Now, when t is equal to 0, let's look at our initial condition right here. Okay, so our initial condition here for number 2 was this guy right here, e to the x, right?
Yeah.
Okay, so now when t equals 0, then we need g of gamma x to equal e to the x.
Okay.
Right?
Yeah.
Okay. So now let's start picking what the alpha, beta, delta, and gammas need to be, okay? So for simplicity here, I'm going to pick my the gamma just to be 1 now. I can see that, right? If I make that 1, then the G comes out nicely to be e to the x. So
Okay.
now we'll let the gamma equal 1, right? And then what would I have to pick the delta to be?
0.
Well, looking back at this equation right here, what do you think I'm going to have to pick the delta to be?
Okay. -5.
-5, right?
Yeah.
Okay. All right, so I have that. So my, let's see, so Z is going to be this, so therefore Z equals, all right, so what's Z going to be? You tell me. So Z, the function Z is then going to be what? E to the,
Okay, so gamma is 1.
mhm,
So it's x minus 5t.
5t,
Yeah.
like that, right?
Yep.
Okay. Now it looks like we have some freedom with the alpha and beta. We actually were not forced to pick alpha and beta to be anything. We didn't need to, but some of the other problems you may have to. So
Right.
now let's just check out that this is actually a solution to our original problem. Now our original problem was up here. It was what? ut plus 5ux equals 0, right?
Yeah.
Okay, let's check out. If I differentiate this with respect to t, right? Oh, and I changed it to z's instead of u's. Okay, do you see
I know.
that?
Yeah. I know
Yeah,
what you mean.
right, all the way back here, I changed the u
Hey,
into a
you,
z.
you didn't
Should
confuse
have
me.
said something. Okay.
You're okay.
So now let's just check this out. So zt 5zx. Okay. So zt is going to be, if I differentiate this with respect to t, I'm going to get -5 e to the x minus 5t, right?
Mhm.
That's my zt. And zx, if I differentiate this with respect to x, I'm going to get e to the x minus 5t. That's zx. And yeah, it does satisfy this equation up here, right? See, if I multiply this by 5, the zx, multiply by 5, and add it to the zt, I get back 0, right?
Yeah.
Now let's check out the boundary condition. So if I look at z of x comma 0, if I put 0 in for t, I do get back, put 0 in for t right here, I do get back e to the 0, or just e to the x.
Right. Okay, that makes
Right?
sense. Yeah.
Okay. All right. Now, you need to do 3, 4, and 5 in a similar manner, okay?
Yeah.
Now, we did one very similar to, let's see. Well, let's see, which one did we do here? We did one that was sort of similar to number 5 in class, except we didn't have a t in front.
Right.
We did a ut plus aux plus b times u. Okay, so it's going to be a little different. Give that one a shot, okay?
Yeah. That.
Actually, number 3, if you look, oh yeah, number 3 is actually going to be actually that one right here. Number 3 is actually just like the one we did in class, but instead of the A and B, I put constants. We have constants in there like -1 and 6, okay?
Right.
So this one here, number 3, is virtually identical to the one that we did in class, except instead of an A, you have a -1, and instead of a B, you have a 6. And
Yeah.
you have a cosine x instead of a general f of x.
Yeah. We never really actually finished that problem. Um, and I'm just kind of confused what you do with that plus 6u right there. That's
Okay. I thought we had finished that. If not, I must have forgot that we didn't finish that. We must have gotten partway through that at the end of class and then didn't finish it the next day. Is that right?
Yeah, it was a Thursday, and then we got back this past.
Well, if I do that, just yell at me.
Oh, it's okay.
Say, hey, we didn't do that one. Okay, I thought we had finished it. Okay, well, all right. So for that one,
I think we,
look back in your notes. You see, you should. Let's see. So, yeah, yeah, yeah. So similar. We want to pick a transformation in which this is true. So that gets transformed into that, right? Okay.
yep.
Yeah. Now, what we end up with are equations like this. If we, this guy right here, that should equal all right, and then plus, right, and those come from these transformation equations, that we have partial with respect to x being like that, and partial with respect to t. And that should be an s. Okay. Now let me double check here. So if I multiply the x all of this with respect to a and add, yeah, I get an a here. So if I multiply this here by an a, we get an a and an a right there, and those two guys are coming out here and here. Yeah, okay, so we're good, right? Okay. Then what you want to do is okay. So what do I want to pick this to be?
1.
So I'll pick that to be 1, and this guy right here will pick to be 0 again. Okay, so we'll do it like that. Yeah, so then what we have is so then this guy right here, going to pick that to be an alpha. This one right here to be a beta. Let's see, and then I'm going to pick this one here to be a gamma and a delta. This guy right here will be a gamma, and this one right here will be a delta. Okay, and so then what we have is oh, yeah, now my a, what is my a in this case? -1, right?
Mm-hmm.
This is number 3 we're doing, yeah. So just remember the a is -1 here, okay?
Okay.
All right. So then what we get is Yeah. A alpha plus beta must be 1, and A gamma plus delta must be 0. And we also want that okay, so this guy right here, okay, so that's alpha. Okay, well, I'm not going to write all those equations out. Let's just say W equals alpha x plus beta t from these equations, and the S is going to be gamma x plus delta t, right?
Mm-hmm.
Okay. All right. Now, okay, so we have freedom to choose the alpha, beta, gamma, and delta. Now, if we choose them to satisfy these equations here, then this operator right here will be turned into partial with respect to W. Okay, so then what we get is our differential equation then turns into this. So therefore, partial, so I guess I'll use Z's here. Yeah, partial Z with respect to T plus A partial Z with respect to X plus BZ. That gets turned into partial Z with respect to W plus BZ, and that all has to equal 0. Okay?
Okay.
All right?
Yep.
Now, keep in mind the A is -1, the B is 6 in this case. Okay, so we'll just substitute those in later. I'm just leaving them in. Okay?
Okay.
So what we get then is if we solve this equation right here for Z, okay, that equation will imply let's see, we should get something like this, that Z is going to be C, some constant that's dependent on S, e to the negative B times W.
We do that with separate.
Separation of variables, right? So you take this equation right here, I'll just do it right up here. So when you separate out the variables, you get partial Z over Z equals B partial W. Now when you integrate, so you're going to get the ln absolute value Z equals B W plus some constant. And then you take E of both sides, right? And you end up with a Z equaling some constant E to the BW. Let's see, do I need a negative in here? Yeah, I do need a negative right there, and right there, and right there. Okay?
Okay.
Now that constant could be a function of S because we have that other variable in here, right? So that C is actually a function of S.
Okay.
All right? Now here's the trick here with this one. Okay, so we have that down there. Now let's bring into play our initial condition, okay?
Okay.
So now, let's see, do we want to do that yet? Well, let's put in, yeah, okay, before we do the initial condition, which was cosine x, okay, okay. Let's put what the s and w's are in place of x and t's, okay?
Okay.
So now my z, so now the z is equal to C, and the S was what? Gamma X plus delta T.
Yep.
E, and the W is alpha X plus beta T. So it's going to be E to the B, negative B, or now B is 6 in this case, remember, in your case, right?
Yeah.
And we're going to have alpha X plus beta T. There's my Z, but now here, now you need to bring into play the initial conditions, right? So Z of, if I put 0 in for T, I get this, X, Z of X comma 0 equals C gamma X E to the negative B times alpha T.
Yep.
Right? Okay, now I'm going to ask you a question here.
Wait, you mean alpha X, right?
Alpha X.
Yeah, there you go. Yeah.
All right. Now, oh, and what's this supposed to equal?
Cosine.
Cosine X.
Yep.
Now, we need to figure out what the function C is. Okay. What would be the easy? Now we have some freedom of choice with these alpha, beta, deltas, and gammas, right?
Yeah.
So what could we pick the, what do you think you'd want to pick them to be in order to find that constant C, that function C? C is some function.
Right.
What do you think you'd pick the alpha and gamma to be?
Alpha equals 0.
Yeah, I think that would be nice and easy because then this term would go to, so let's let alpha be 0. So then this term here would just go away and become 1.
Right.
That's if alpha equals 0. Okay, and then what do you think you'd do?
Gamma equals 1.
Yeah, we're going to let gamma be 1. Then we know what our function C is. So C of X is just the cosine of X.
Okay.
Now, if alpha is 1, okay, then what is beta going to be?
Wait, if alpha is 1, let me see here. Alpha is 1. Beta is going to be negative 1?
Well, see, looking back at my equations here, A times alpha plus beta equals 1.
Oh, right. So,
Right? And alpha, we said, alpha was 0, right?
yeah,
Oh, okay. So what's beta?
Oh, 1.
Yeah, so beta's 1.
Yeah.
Okay. And what did you pick gamma to be? 1. Okay, so if you pick gamma to be 1, what's delta going to be?
Okay, gamma's 1. Let me see here. I'm sorry. Negative 1.
Negative 1. Yeah, let's see. Wait a minute. If gamma is 1, hold on. Delta should be
Oh, wait, A is negative 1.
negative A, right?
Yeah.
Oh,
Yeah.
I see. You put the negative 1 in there. Let's just leave the A in there for now. Okay. So if the gamma is 1, delta is negative A.
Right.
And so delta would be 1 in the case for this function right here, okay?
Yeah.
So tell me then, what would my function Z equal?
Z of xt. That's going to equal.
Cosine of?
Okay, cosine of x. Where's that? Minus at.
And then times?
Times e to the negative b.
And alpha was 0, so we don't have any x term, right? So it's just going to be, beta was what?
1. So it's
1.
t.
So t.
Yeah.
All right. Now, I claim that that is a solution to this differential equation. That should be a solution to Zx, wait a minute, no, Zt rather. That should be a solution to this. Zt plus, oops, excuse me,
No problem.
plus AZx plus BZ equaling 0, right?
Yeah.
Okay, now check it out. Let's see, let's double check that. If I differentiate all this with respect to t, I'm going to have to use the product rule here. Okay, let me go back up here then. See, so derivative of that with respect to t is going to be the cosine of the stuff in there, e to the negative bt times negative b. Okay, so it's going to be negative bt times negative b plus, I'm using the product rule, right? I'm differentiating with respect to t first, okay?
Oh, right, yeah.
Plus, then this times the derivative of this with respect to t, and that's going to give me negative a, actually positive a, because the derivative of cosine is negative sine. I'm going to end up with a sine of all that stuff, e to the negative bt. All right, now that's the z, this is all zt right here. Now plus, now I'm going to have a times zx, so I have to differentiate this with respect to x. And so that's going to give me derivative of cosine is negative sine, so that's going to give me negative a sine of all that stuff, e to the negative bt. All right. Plus, and then the final term is the bz, so b times the cosine of all that stuff, e to the negative bt. Okay, now, my handwriting up here is a little bit sloppy, but can you see how everything cancels?
Let's see. Oh, yeah.
This guy cancels with
Yep.
this one down here, and these two terms,
Go bye-bye.
and I get 0.
Ooh.
Yeah,
Cool.
we did it right. Oh,
Yeah.
let's check the boundary condition. U of x comma 0 should be the cosine, right? So if I plug 0 in down here for t,
Get cosine.
I get cosine. Look at that. Yep,
Cool.
we get cosine, right? And there you
Okay.
go. Okay, so there we go. We solved that partial differential equation using that method of characteristics. Works pretty neat.
That's
Pretty
cool.
well.
Good.
Okay. All right. Now the other ones, do you want to try those on your own then, right?
Yeah, I think I'll be okay
Without
with
any, right? You should be able to do those now.
Yeah.
4, 5, and it looks like number 6 is probably a D'Alembert type problem.
Yeah, that one shouldn't be a problem. I'm
Okay.
looking at the notes, and that looks fine.
Yeah. Okay. And just remember for this one, yeah, what our A was -1 and our B was 6. So
That's
okay.
right. Yep.
Yeah. So that finishes that one in the homework. Sorry if I didn't finish that
Okay.
in class, but that's the completed. Okay. So now it's completed. What we went over here actually completes that problem. And okay.
Cool. Thank you.
All right. Now, is that all you needed then today?
I think so.
Okay. Yeah. If you need anything else, you have till Thursday, so we can talk a little bit tomorrow or on Wednesday. Okay.
Okay. Sounds good.
All right. I'm going to sign off then, and I'll post this up on Moodle for other people to see. Okay.
All right.
So you'll be famous. You'll be a Moodle star, right?
Yeah, I can't wait. Ooh.
Yeah, I can't wait. There you go. All right, Damien. I'll see you tomorrow.
Yeah, man. Have a good day.
Okay. Bye.
Bye-bye.